All right, let's get right into it. Deep down, at the very core of some of the most powerful quantum algorithms, there's this this maneuver that's so incredibly clever, it honestly feels like a magic trick. It's this beautiful piece of quantum sleight of hand called Phase Kickback. And you know what? We're going to pull back the curtain and see exactly how it's done. So here's the big puzzle. I want you to imagine you've got this machine, right? You put an input in one slot, and an output pops out of another. Now, how could you possibly change that original input? Just by messing with the output, without ever directly touching the input again. I mean, in our everyday world, that sounds completely impossible. But in the quantum world, well, it's not only possible, it's absolutely essential. To get our heads around this trick, we first need to meet the star of the show, the quantum oracle. Just think of an oracle as a specialized black box. You give it an input, we'll call it x, and it computes some function, f of x. The key thing here is we don't need to know how it does it. We don't get to peek inside the box. We just trust that it works. It's a really fundamental tool in quantum computing. Okay, so this is how the oracle normally behaves. It's a two-part system. It takes in two different inputs. You've got the top one, which we call ket x, that holds our main input. And then there's the bottom one, ket y, that kind of acts as an answer sheet. The oracle computes the function f of x, and then it combines that result with the answer sheet using a quantum version of addition. But the really important thing here is what doesn't change. And this is the crucial part. Look closely at that input, qubit x. It goes in, and it comes right back out, completely unchanged. The oracle's entire operation, all the action, happens on that separate second qubit. Just remember that. It's the key to this whole thing. All right, so we've got our oracle. Now we need the secret ingredient that really makes the magic happen. So we're going to bring in something called an ancillary qubit. You can think of it as a helper, a magician's assistant, really. We bring it in to help with one specific part of the calculation, and our standard oracle is going to act on this helper qubit. And here it is, this secret sauce. Instead of just setting up that helper qubit in a standard state like 0 or 1, we're going to put it into a very, very specific superposition. We're going to set it to the state known as ket minus. And this formula right here shows you exactly what makes it so special. See, it's an equal mix of ket 0 and ket 1, but, and this is everything, there's a minus sign between them. That little negative phase, that is the pivot point for the entire trick. Okay, the pieces are on the board. We've got our oracle and we've got our secret ingredient. So let's put them together and watch the magic unfold right in the mathematics. So we're sending our input ket x into the oracle, but this time that helper qubit is prepared in our special ket minus state. Okay, so one of two things can happen here. First case, what if our function f of x equals 0? Well, the oracle is supposed to add 0 to our helper qubit, and, well, adding 0 doesn't do anything, right? So the whole state just comes out completely unchanged. But now for the fun part. What if f of x equals 1? The oracle's job is to add 1 to our helper qubit. This flips the ket 0 and ket 1 parts. So our state, which was ket 0 minus ket 1, becomes ket 1 minus ket 0. Now let's do a tiny bit of algebra here. Ket 1 minus ket 0 is the exact same thing as writing minus 1 times ket 0 minus ket 1. So what's happened? Amazingly, our helper qubit is right back in the same ket minus state it started in, but an overall negative sign, a phase, has just appeared out front. And there it is. That's the kickback. The information about the function's output, was it a 0 or a 1, it didn't stay on the helper qubit. Instead, it was kicked back as a phase, a little plus or minus sign, onto the original input state, ket x, the one we never even directly touched. And this single, totally elegant equation you see here, it summarizes that entire effect perfectly. The oracle's operation on our combined state results in minus 1, raised to the power of the function's output, f of x, all multiplied by our original input state. Just think about that for a second. If f of x is 0, minus 1 to the power of 0 is just 1. Nothing changes. But if f of x is 1, minus 1 to the power of 1 is minus 1, and the phase of our input flips. All that incredible behavior captured in one simple, beautiful, powerful expression. So that's a really neat mathematical trick, right? But why does it actually matter? Let's take a look at how this one clever move builds into something truly revolutionary. This is the true power of phase kickback. See, if your input, ket x, is actually a superposition of many different values at once, you can use the oracle to flip the phase of only the specific values that are the solutions to your problem. You're essentially marking the right answers, putting a little tag on them inside the quantum state, all without having to destroy that delicate superposition by looking at it. And this isn't some obscure one-off technique. No way. This is the fundamental engine that drives so many of the most famous quantum algorithms we have. We're talking Deutsch-Jozsa, which first proved quantum advantage, Grover's algorithm for searching, and yeah, even Shor's algorithm for factoring huge numbers. They all rely on this core principle of phase kickback. I mean, just take a look at this circuit for the Deutsch algorithm. On that bottom wire, you can see the X and Hadamard gates. That's what prepares our helper qubit in that special ket minus state we talked about. Then, boom, the UF gate, our oracle, performs the kickback. The result of the function gets kicked onto the top qubit as a phase, which is then processed to give us the final answer. It's phase kickback, right there, live in action. So, the next time you hear about quantum computers breaking codes or discovering new medicines, I want you to remember this elegant little trick. It all starts right here, with a simple phase flip. It really makes you wonder, doesn't it? What other seemingly impossible problems could be solved, all thanks to this one clever bit of quantum sleight of hand?